If there is a one lone pair of electron, we are continuing with the shapes of covalent molecules. What we have done up till now, we are going to continue with the next part. Okay, so what I said before, that if I quickly review the previous lecture, what it says that the electron pairs around the central atom determine the shape of the molecule, right? So if there are two electron pairs around the central atom and both of them are the bond pairs, then the shape will be what? Linear. If there are three bond pairs, diagonal planar. If there are four bond pairs, tetrahedral. If the lone pair comes in, two bond, one lone, bent angular V-shaped with a bond angle of 117.5. And then if there are three bond, one lone, trigonal pyramidal with a bond angle of EI. And what about two bond, two lone? Bent angular, again V-shaped, non-linear with angle of 104.5. Today we are further continuing with the molecule PCl5. Please look at the PCl5. Phosphorus has 1, 2, 3, 4, 5. So phosphorus has 5 bond pairs, bacho. 5 bond pairs, okay? So here is the phosphorus. Look, 1 Cl, 1 Cl, 1 Cl. So how many bond pairs here now? 3. And what is the angle between them? 120. Can you see the angle? Yes. What is the angle? 120. And the fourth one is on the top. And fifth one is here. Okay? So 90. Yes. So the one which are on the top, they have the 90 with the one which are at the 120. Right? So there are two angles in this case. There are 90 and there is a 120. Okay? For the 90 degree, 90 and 120. Okay? Trigonal. Shape name is trigonal bipyramidal. Shape name is trigonal bipyramidal. Okay? So whenever there are 5 bond pairs, you have to go and add in the table. Whenever there are 5 bond pairs, the shape is trigonal bipyramidal and the bond angle is 90 and 120. Okay? Okay? 90 and 120. Please go and handle in the electron pairs. 5 bond pairs. 5 lone pairs, 0, and the shape is known as trigonal bipyramidal with 2 angles. 90 and 120, bacho. On purpose, I am not drawing it 3D. We don't need it. So there are 3 actually. 3 on here. Look, there are 3 here with angle of 120 and 1 on the top and 1 underneath. Okay, that makes 2 angles, 90 and 120. Okay, the next one is SF6, sulfur hexafluoride. So 1, 2, 3, 4, 5, 6. This is SF6. Right, so there are 6 bond pairs around the central atom. No lone pair, right? So if you look at them, look at the shape. Please stop writing. If you look at the shape, it's like this. There are, look, there is the fluorine. Here is the fluorine. Okay. So there are 2 fluorines. Okay. And there are 2 more here. So these are the 4, 1 on the top and 1 underneath. So look at this then. What is this shape name known as? I've shown it in a 3D. This shape is known as, yes, it's a octahedral with a bond angle of 90 degrees. Okay. So whenever, add in the table, whenever there are 6 electron pairs, 6 bond pairs, 0 lone pair, octahedral shape with a bond angle of only 1, that is 90. Okay. These all bond angles are 90. Yeah. Now there is a one more case left in this case. For example, look at XCF4. You have to draw the dot and cross for XCF4, bacho. XCF4. Xenon is in group 8. 1, 2, 3, 4, 5, 6, 7, 8. And there is a 1 electron here, 1 here, 1 here. So 1, 2, 3, and then 4. So how many bond pairs? Look at this. 1, 2, 3, 4 bond pairs. And how many lone pairs? 2 lone pairs. Here is the lone pair, and here is the lone pair. So what is then a shape? 2 bond, 1 lone. Please pay attention. So actually, here is the fluorine. Here is the fluorine. Here is the fluorine. Here is the fluorine. Okay. So yes, the one who were on the top now, they actually turned into this. Okay. So this is square planar with a bond angle of what? Bond angle is 90 degrees. Okay. Bond angle is always 90 degrees. Okay. So got it? So this is 6 in total, 4 bond pair, 2 lone pairs, square planar with a bond angle of what? 90 degrees. And the example is XCF4. Right. So that's all the cases which we have. Right. So now you have to keep the table in front of you. I'm going to give you a question. It's a very straightforward. You just need to learn this table, and then you can easily figure out the angles and diagrams. Okay. Now I'm going to give you a question here. All types we have done. If you can see, I can go through it quickly. For example, we had it in the last class here. Look at this, for example, here. See, this is the table. Okay, here is the bond pair, lone pair. Today we added 2 more with the 5, 5, 0, with the 6, 6, 0, and with the 6, 4, 2. Okay, 3 more we added. One is this is called trigonal, bipyramidal with a bond angle of 90 and 120. 6 bond pairs. This is octahedral with a bond angle of 90. And then this is square planar with a bond angle of 90. Okay. So here are the complete shapes. The complete table is right here. So 2 bond pair, 3 bond pair, 3 bond pair with 2 bond and 1 lone, 4, and then 3 cases in 4, 4 bond pair, 3 bond pair, and 2 lone pair, 5 bond pair, 5 electron pair, only 1 case, 6 bond pair, we have 2 cases. Okay. Now I'm going to give you a question here. If you want, you can take the screenshot and keep it in front of you. And then here is the question. Look at this. If I give you a molecule here and ask you, what are these angles X, Y, and Z? Please identify the angles X, Y, and Z. Here is the X. Here is the Y. Here is the Z. and here is the P. Okay, but you have to tell me the angles HCH, which I'm labeling X. Sorry. X, Y, and Z. What is the angle X? What is the angle Y? What is the angle Z? What is the angle P? Okay, now it looks like 90, but we don't have to look at the geometrically how it looks like. We have to go for the electron pairs around it. One line is one bond pair, one bond pair, one bond pair, one bond pair. So three highlighted areas around this carbon bond pairs. Four bond pairs. When they have four bond pairs, so what is the angle? 109.5 tetrahedral. Okay. What about this? 1, 2, 3, 4. What about this? Again 109.5. You don't have to see how it looks like. You have to see what is the angle. Both these shapes will be tetrahedral. Okay. What about the next one? 120. What about this? 120. Why 120? It looks like 180. We don't see how it look like. We see there is a one bond pair around this carbon, one bond pair, and double bond is also considered as one bond pair. Carbon doesn't have any lone pair. So there are three bond pairs around the carbon, which makes 120, 120, and the shape is trigonal planar. Okay. What about the last one? 180? 120? No. It's the one. The oxygen, you can see the two bond pairs, but I know you might remember the oxygen's octet is completed by the rest of lone pairs. So how many lone pairs? Two, and two bond pairs. What is the angle? Non-linear. With the angle of non-linear. Okay. Got it? 117 should be for three bond, then one lone. In oxygen, you see there are two bond pairs and two lone pairs. Okay, next, look at this. And look at this. Please, you have to tell these angles. This is X, this is Y, this is Z. Please tell me the angle X, Y, and Z. 112 bond, so 3 totals. X, Y, and Z. 170.5 plus 1. Non-linear. X, Y, and Z. What is X? What is X? 107. 117.5. Anyone else? Unfortunately, yes. If you look at the nitrogen, nitrogen always has one lone pair. If it has one lone pair and 1, 2, 3 bond pairs. So one lone, 3 bond, all the angles between the bonds, both X and Y should be 107. So both of them are kids 107. Okay? Both of them are 107. Then what about the other side? Obviously, das nitrogen also contain one lone pair. Then what do you think? 107. 3 bond. 3 bond, one lone. 107. 107. So all three angles are the same. Right? Because both nitrogens have 3 bond pairs and one lone pairs. So once they have three bond pair, one lone pairs, you know what is the, okay? Is it clear? Yes, sir. So this is how you look at the bond pairs and lone pairs to look at the shape. We do not generally see how they look like. Okay. You have to immediately go back, draw the dot and cross, and figure out how many bond pairs and how many lone pairs around the central atom. And then you would be able to identify this. With this, we have come to end of this shapes of covalent molecules, right? So the after the shapes of covalent molecules, we have the next type is bond polarity. So please give a heading, bond polarity. The charge separation. Please write down, I'll explain. The charge separation which takes place due to the difference of electronegativities between the bonded atoms is known as bond polarity. Now let me explain this. What did I write? Let me explain. Just 1 minute, Bacho, I'm rejoining. When a covalent bond is formed between two atoms, like hydrogens, both of them are hydrogen, let's say. I believe both of them are hydrogen. And the bond is formed by the sharing of electrons like this. The bond is formed by sharing of electrons between two hydrogen atoms like this. Uh, Let me draw it. both these atoms pull the electron pairs towards itself. This force is known as electronegativity. Both atoms are same, so the electron pair is going to remain in the center, right? So no charge separation. Okay. But on the other hand, when hydrogen and chlorine are bonded together, the electron pair that is shared between two atoms is not going to be in the center. It is still a covalent bond, but the electron pair gets close to what? Cl. As a result, what happens? It's a still covalent bond. I'm explaining myself, it's a still a covalent bond. But in this particular case, when the electron pair is now very close to the chlorine, a bit away from the hydrogen, yes, the molecule that is formed. Now, please mind this difference. It's not about the bond. It's the molecule that is formed here. The molecule of what? HCl. The molecule of HCl that is formed here will have partial or slight negative charge on this side where the electron is close to, and positive or slight positive charge on the side which is the electron is away. So it's not about the bond, it's about the resultant HCl molecule. It has developed two poles, positive pole and negative pole. That's why we call it a dipolar molecule. What we call it? Dipolar, or we use the word polar molecule. What do we use? Polar. So what I'm trying to say is when the bond is formed between two atoms, where the electronegativity difference is obviously greater than 0, less than 1.7, the one that, no, that's the next part. Yeah, that's the next part. The one that is more electronegativity, the electron pair goes towards close to that atom. So that atom side of the molecule gets slight negative charge, partial negative charge, which is represented by this symbol like an infinity, S from the top, and the last part has one more turn, right? And this is slight negative, and this is slight or partial positive. On the other hand, in this case, look at this. This molecule of H2 that is formed, it has no such phenomena. Charges are there because hydrogen molecule also contains electrons and protons. But that molecule, if you look in the charge context, looks like this, in which negative is outside and positive is inside. No charge separation taking place in this. And this type of molecule is known as non-polar molecule, okay? Or having no dipole, okay? So this is the difference. This is again, we are talking, let me remind you, we are still talking about the covalent bond and which structure? Simple molecular structure. This is the covalent bond with simple molecular structure, which have the compounds consist of tiny molecules, 2, 3, 4, 5, or the number of atoms which we count on, like 10, 12, 15, 20, 20, 30, something like this. They combine and make a small molecule. We are talking about those molecules. In the last part, we discussed their shapes. Now we are seeing their charges. Okay? So apparently we believe that the covalent molecules do not have charges. Now we got to know, no, they have the charges. They do have the charges. Okay? And they look like this. Is it clear? Okay, now from here on, whenever you look at the covalent molecules, you have to look at like this. Is it polar or a non-polar? Does it have a dipole or does it have no dipole? Okay? So as far as this definition is concerned, which I have just told you, you can easily imagine if the bond is formed between two similar atoms, like this, you can easily guess that these molecules like Cl2, O2, N2, they won't have any charge separation. Why won't they have any charge separation? Why do you think so? Because both atoms are the same. Their electronegativities are same, equal. So they pull the electrons towards each other equally. So the electron pair is not going to go anywhere. The shared pair I'm talking about, it's going to be in the center. So all these molecules which are formed as a result of what? Two atoms, two similar atoms. This is known as non-polar molecules. Okay. On the other hand, if you have a different atoms like C and O, No, I know oxygen's electronegativity is more than carbon. How we know? We have learned this in the previous section. We have learned the electronegativity. Yes, FON, fluorine, oxygen, nitrogen are highly electronegative atoms. So in this case, oxygen is higher. So that side of the molecule gets slight negative, and the other side of the molecule, the carbon side, slight positive. Okay. Similarly, if you can go on, for example, ICl, iodine is more less electronegative, Cl is more electronegative. So the molecule of ICl is polar again, right? So whenever in a diatomic molecules, that's pretty much straightforward. In a diatomic molecule, if two similar atoms are there, it's a non-polar. If two different atoms are there, the molecule is definitely polar. Okay, but this is for the case of diatomic. We say that all the molecules are not diatomic. Like ammonia is not diatomic molecule. How many atoms? Diatomic mean two atoms. And how many atoms in the ammonia molecule you can see? How many? Four atoms. Methane, how many? Five atoms. So the molecules like this, how you are going to determine or deduce? Vector addition. Yes. So we have to have a different procedure for that, right? Let's see what is that. Okay. You can put a star and write for the molecules which are not diatomic, which are bigger, are not diatomic. For example, look, uh, let's start with CO2, three atoms, carbon dioxide. Now, if I look at the carbon dioxide, we have to obviously draw the dot and cross, and then we have to look at the shape. Carbon dioxide, after drawing dot and cross and looking the shape in the previous part, I got to know it's a linear. Now, if I go into that, please stop writing and pay attention. Here it is. Out of oxygen and carbon, oxygen has more electronegativity. Am I right? So this side is going to be partial, and this side is. On the other hand, if you go to the left side, same is the case. Right? Now, how would I decide that this molecule is going to be a polar or non-polar? Because it has more than one polar bonds, more than one polar sides. In this particular case, listen carefully what I'm going to say. You have to add up the bond polarities. You have to add up these bond polarities or these poles of the molecules. How to add up? Actually, what we do, we consider a bond polarity as a vector quantity. As a vector quantity, every vector quantity has two things, direction and magnitude. Direction is always positive to negative. So this is the one vector. And this is another vector. Right? And the magnitude of vector is the difference of electronegativities. What is the magnitude? Difference. So there is a maths going on, okay? We should have the values, and I do have 3.5 for this and 3 for this, the electronegativities. Now, what is the difference? What is the vector value for this? 0.5. And what is the vector value for this? Now, the two vectors which are opposite in direction and same in magnitude, if you add them up by vector addition, what will be the answer? 0. So it means the overall bond polarity which is also known as, in a technical term, known as dipole moment, right, is 0. Hence, this molecule is not polar, hence non-polar. So I hope you understand this. Okay, a lot of information is needed to determine the molecule is polar. A lot of information mean you need to have the electronegativities of all the atoms involved. Then you should be able to draw the vectors, and then you should be able to add those vectors up. And before that, you should be able to understand or figure out the shape of the molecule. Because if you don't know the shape of the molecule, then it will be hard. For example, the similar looking molecule, sulfur dioxide, it was carbon dioxide. If I ask you about the sulfur dioxide, look at this. It's the same like carbon dioxide. So if I ask you what is the shape of sulfur, is it a polar molecule or not? The sulfur dioxide. Non-polar? Okay, why? Here is the sulfur dioxide, like this. Right? Does it look like the same? But if I can remind you, sulfur dioxide is not linear. Carbon dioxide was linear in shape. Sulfur dioxide has one lone pair along with two bond pairs. And because of this lone pair, what happens? It's a non-linear. When it's a non-linear, and I look at this is partial negative. This is now here is the one vector. Here is the one vector with angle of 117. Do you think now still like a carbon dioxide as these two vectors and these two vectors is still sum zero? No. These two vectors can't have sum zero because they are not in opposite direction. They are in two different directions with angle of 117.5. So once you add them up, both of them are pulling down. They can't cancel each other's effect. They can't be zero. So sulfur dioxide is a polar molecule. Okay? And how this polar looks like, look at this. If you want to understand how this polar looks like, this side, the top side is partial positive. The downsides are partial negative. So in overall, if you look, the downside is partial negative and the top side is what? Partial positive. Okay? Still two poles. Okay? Not more than two poles. So I hope you understand that if you do not know the shape, you won't be able to figure out. Shape should be linear. Then they cancel out each other's effect. Then the vector sum will be zero. Right? For example, if I give you, look at this, CCl4. What do you think about this? CCl4. Here is the carbon and 4Cl attached here. 1, 2, 3, 4. Look at this. Yes, they cancel out each other's effect because they are the tetrahedral. They cancel out each other's effect, right? So CCl4 is what? Non-polar. Okay? CCl4 is non-polar. All right? But on the other hand, what about NH3? NH3 is like this. This H, and this H. What do you think about this? Sorry? Yes. Why? Because this vector, they're always positive to negative. Here is one vector, here is another, here is another. These three vectors, do you think they can add up to zero? They are all going in one direction. They can't be zero, right? So this is how you determine the over. And what do you call it once you add the vectors up? The answer which you get, the sum of the bond polarities or overall bond polarity is also known as dipole moment. So for all those molecules with the dipole moment zero are the non-polar. For all those molecules with the dipole moment positive are the polars, right? So, but on the other hand, what we believe, okay, fine, we can do it. Thank you very much. But we need a lot of information to get this information out of this phenomena. We need to have the shapes. We need to have everything. Is there any shortcut? We say yes. There is a shortcut. When in exams, the examiners are not interested you to actually figure out, do all the math work. They just ask you, is it a polar or non-polar? You have done a shortcut. What is that shortcut? Please write down. There are two rules which you have to follow just to see it's a polar or non-polar. Rule 1, that's a straightforward. If central atom of a molecule has lone pair, it's a polar molecule. So you do not need to do anything. Just draw the dot and cross and see the central atom of molecule. If it has a lone pair, no need to draw the shape, no need to look at the bond polarities, nothing. Straightforwardly, it's a polar molecule. For example, look, ammonia molecule. If I look at ammonia, the central atom is nitrogen, it does have lone pair. Water, the central atom oxygen has two lone pair. Sulfur dioxide, central atom sulfur has lone pair. So whenever you draw the dot and cross and you see the central atom containing lone pair, you don't bother to do anything. You say it's a polar molecule. I know it. Okay. On the other hand, if there is no lone pair with the central atom, then there are two cases. Still, they can be a polar, even if they don't have lone pair. How? Look, for example, in the second case, if no lone pair with central atom, then we have two cases. Case one, all atoms around central, same, non-polar. Even one is different. It's a polar. For example, look, carbon doesn't have lone pair. If it has 4 chlorine around it, if it has 3 chlorine and 1 hydrogen, it becomes what? I hope you understand, okay? For example, CH4 and CH2Cl2. Now, the central atom has all 4 hydrogens around it. It's a non-polar. If 2 hydrogen and 2 chlorine, it's a polar. Right? Keep in mind the carbon doesn't have any lone pair. Right? So this is the shortest way of getting it. Right? And one last thing, more polar and less polar. More and less polar. If you have two molecules polar, like HCl, like HF, and you have to determine out of these two who is more polar, obviously you have to look at the electronegativity difference. Over here, the difference is 2.5 and 3.5. What is the difference? 1. Over here, the difference is 2.5 and 4. What is the difference? Which is more polar than? Yes. So it means HF is more polar. So what I'm trying to say, whenever he's asking you for the more and less polar, so you say, you look at the bond polarities, the difference, and then you decide whosoever has more difference, higher number in the difference of electronegativity would be more polar, and whosoever has less would be a less. Yeah, they'll be given. All the electronegativity values are always given to you. Okay, you just need to understand the phenomena of the difference in the electronegativity. I hope it's all clear, right? Okay, thank you very much. That's all from my side for today. We'll continue this. We are left with intermolecular forces, and then we'll move on. Yes.